In this video, we're going to be covering the basics of growth and decay models. For growth and decay models, you will generally see an equation that looks of the form A equals A sub 0 e to the kt. Again, keep in mind this is very close to A equals P e to the RT. The only difference is with this formula here, you'll probably be referring to money, in which case money is normally an interest rate such that that rate is growing at a certain percentage. Sorry, the amount of money is growing at a certain percentage, and that rate is calculated utilizing this formula. For our growth and decay models, we're going to refer to this formula, or in some other cases you might see it in this way, y equals a e to the kt. You might see it in a number of other possible ways. What's important here is that it's generally an exponential equation such that this value here is your starting amount, this t represents time, and that time for these formulas with growth and decay are in reference to the situation you've been given at hand, while this value over here for the money or economic problems will almost always refer to t as a year. So t is the number of years that you're investing the money. Over here, t could be days, it could be minutes, it could be seconds. It entirely depends on the growth rate of the thing or the decay rate of the object that we're talking about. So in this situation, k is going to be either a positive number or a negative number. If it's a positive number, we're talking about a growth problem, in which case, again, the value of what we have is increasing, the number of the population that we have is increasing. If it's a negative number, then we have a decay problem. In most cases, you might refer to radioactive material, in which case, if k is a negative, we have that radioactive material decaying over a certain amount of time. So, with this situation, let's look at an example. One of the major examples we talk about is half-life. Keep in mind that half-life is specifically correlated to the number of years, or the number of days, the number of minutes, the number of weeks, whatever it is we're talking about, the number of the time, we're going to go ahead and refer to years in this particular case, the number of years it takes for half of the material that was there to dissipate. So in radioactive material concepts, it's not that the material is disappearing, it's the radioactive material is dissipating, or again, assimilating with the materials around it and therefore no longer being radioactive. So let's consider a situation such that an object or a radioactive material, a substance, has a half-life of 32 years. What this means is that after 32 years, half of the amount of material that was there will then be gone. So what we're going to do is we're going to have to calculate, and this is more or less the only information we are generally given. We have to calculate what is the k value that correlates with a half-life of 32 years. So in this case, t equals 32. But keep in mind that if we have a equals a certain amount, that's the amount we have. A naught is equal to the initial amount, and again we generally refer to this as a sub 0 or a naught. If a naught is the initial amount, then the amount after 32 years should be equal to 1/2 of the initial amount we had. Again, keep in mind that the fact of the half-life refers to how much material is left. Half of that material is going to be left after this amount of time. So what I know to be true in every single half-life problem is that this formula will end up converting to 1/2 of the original amount we started with is equal to the original amount e to the k is what I don't know yet, times t, which is 32 years. So again, I'm plugging in 32 for my time value, I'm plugging in 1/2 of the original amount for my a value, e is a number, a sub 0 is missing, but if I didn't know what it was, I could just plug in 1 here, and it would still all work out to be the same, and I'm solving for k. Most of the questions that refer to half-life identify first, to start off with, identify the exponential decay model that this particular substance adheres to. So once we're here, we can go ahead and divide by a sub 0 and solve for k. If If I start by solving for k, I'm going to have 1/2 is equal to e to the 32k. I'm going to go ahead and just rearrange the exponential terms. And then what I'm going to do is I'm going to say, well, how do I solve this kind of equation? Well, if I've got e to the 32 times k and I want to get k out of the exponent, the function that will remove an exponential function and remove the exponent from the exponential function is a logarithmic function. So for me to manipulate this, I'm going to go ahead and just change its form. Or again, I can take the natural log of both sides. So in this case, I'm going to have the natural log of 1/2 is equal to 32k. Again, the concept is I'm either taking the natural log of both sides, in which case this side just becomes 32k, and this side becomes natural log of 1/2, or I change the form, where my base is e, so that's where the natural log is coming from. Every log is equal to the exponent is 32, and the inside is whatever's left, so that 1/2. So once I'm here, I can divide by 32. So my k value becomes the natural log of 1/2 divided by 32. Now, some of you might be thinking, well, how is this going to be a negative number? Because remember, this is a decay problem, and decay problems should have a k value that's negative. Well, something about the natural log function is that after we hit this point of 1, it is below the x-axis. So everything above the value, x value of 1 in the generic natural log function is positive, but everything between 0 and 1 is a fraction. That fraction value is going to be below the x-axis, and therefore that number is actually negative. Again, well, there's another way that we can see this, such that we use the quotient rule, such that it's natural log of 1 minus the natural log of 2 divided by 32, because the division on the inside becomes a subtraction on the outside. Natural log of 1 is going to be that value of 0, and there it is. Negative natural log of 2 is the value we're playing with. We don't have to do this. This is just a nice little trick to notice that it is going to be negative in the grand scheme of the problem. So what we're going to do now is, again, the first goal was to find the model. So y equals a sub 0. They didn't give me an initial amount to start with, so I don't know what it is. E to the power of my k is either this number right here, and I would generally recommend using this, but if it's asking for me to plug in a decimal value and approximate, I'm going to go ahead and type this value into a calculator and get approximately negative 0.0217. I'm going to round it to 4 decimal places. In some cases, you might have to round it to 6. Some you might have to round it to 3. You're going to want to round it to as many decimal places as possible to get the most accurate answer in the final question. So I'm going to have e to the negative 0.0217 times t. Keep in mind, in these questions, the variable is t. T is the so-called generally unknown. It's the thing that changes. Again, the amount of time is what changes. The rate at which this object decays does not. So this is our generic formula for the half-life substance problem. In most cases, you might be asked, leading up to that then, how much material would be remaining after a certain number of years. If that's the case, you can just go ahead and plug t in. If the question says how much material is remaining after t number of years, you just plug in t. But a more common question that's going to be asked is, how long will it take for, say, 13% of the material is left of the substance. Now, the reason why you might be asking these kinds of questions is specifically because, well, maybe 13% is the acceptable percentage of that radioactive material that won't kill you, is where that breach gap is going to be. So maybe after how many years we need to know, is it going to be for the radioactive material to be only 13%, and therefore we can feel comfortable going in there and scrubbing the rest as individuals, rather than going in there and dying from radiation poisoning. Or maybe 13% is acceptable rate for us to walk in there with suits on. Who knows? The point is that this is the more common question to ask. How long will it take for there to be 13% of the substance remaining? So we need to find out what T is based on 13% of the material remaining. Well, what do we mean by 13% of the material remaining? Well, what we mean is Y should be equal to 13% of the original amount. In other words, 0.13, because that's the decimal representation of a percent, times a sub 0. So this right here is what we're looking for, 0.13 of the original amount. Notice again, in this problem, nowhere were we given the original starting amount that we had. It is possible that we could be given it, but it is not always probable. So once I'm here and I understand that this is what I'm looking for, again, this is what I'm looking for, then I can go ahead and use this formula that I found in the previous step and plug in the information for y. So 0.13 a sub 0 is equal to a sub 0 e to the negative 0.0217 t. I can go ahead and divide both sides by that a sub 0, and you'll notice in this situation, just like the previous one, the initial amount doesn't actually matter. When we're talking about a percentage in terms of decay or growth problems, the amount we actually start with doesn't matter. If we're talking about, well, I want there to be a certain percentage left of that original amount, it's always going to decay at the exact same rate. So over a certain amount of time, it's going to take the exact amount of time for, say, an entire room filled with radioactive material to decay to 50% of it, versus having a small grain of salt in your hand that has that substance. So those two things will decay at the same rate, meaning 50% in both situations will be left over. Half the room will be left versus half that grain of salt will be left. So in this case, we're going to have 0.13 is equal to e to the negative 0.0217 t. We're going to go ahead and solve for t, but in this case, we're going to take that natural log of both sides. Natural log of 0.13 equals to, if I take the natural log of this side, I'm just left with the exponent. I'm going to divide both sides by that value in front of t. And I'm going to get t is equal to this natural log of 0.13. Remembering that a decimal inside the natural log is nothing more than a negative number. So sure enough, I will get a negative number divided by a negative number, which will give me a positive number. Now, I don't have this value calculated off the top of my head here, but in a calculator, we can just go ahead and type this stuff in and get, second, the natural log of 0.13 divided by a negative 0.0217. And that's going to give me approximately 94. Now, this should make sense. What is this value going to correlate to? 94 years. Why years? Because the original problem's time value was years. Keep in mind, if the time value was in weeks, then this value would still be in weeks. So all of these units of measurements should correlate appropriately. Now, does this 94 years make sense? Well, think about it. In 32 years, half of the substance that we started with will be left over. So if I'm looking for 13% of the substance to be left over, it should be almost, well, one iteration of that cycle should bring us down to 50%, another iteration of that cycle should bring us down to 25, and a third iteration of that cycle should bring us down to nearly 12.5 or 13. So you'll notice 32 years times 3 is pretty darn close to 94, and this value should then make sense. And another way to have a more basic understanding is that, yes, this is drastically larger than this number, 3 times almost, and therefore it should correlate that 50% again that's left versus 13% that's left, again, in a decay problem should make mathematical sense. Keep in mind, again, these problems don't have to necessarily be decay problems, they can be growth problems. But the only change between those problems is the fact that my k has to turn out to be a positive number, and we're generally looking for, rather than percentages, but how much is going to be left after a certain amount of time, or how much we're going to have after a certain amount of time, or if we're talking about population growth, how many people are left. How many people, when will a population reach a certain amount after a certain amount of time? But that's your growth and decay model, specifically section 3.5 out of your textbook, and it focuses mostly on the applications of exponential problems with applying logarithmic functions to solve.